from where we left off. Make it full screen. Okay, so we were starting to look at pattern matching, and we had seen this simple example where what we wanted to do is we wanted to print a message that either says the list is empty, or if the list is non-empty, it prints the head. Okay, so the way we did it is define a function called list status that took the list as an input, right? And we used the pattern matching syntax, which is match with, use the list L, and match with an empty pattern. The way to read this is if the list is empty, then print end line list is empty. If the list is non-empty, we match with the cons pattern, right? And it takes two parameters, and the first one is a variable where we which associates itself with the head, and the second one is the tail, right? And we say, okay, so if it is non-empty, then it must have a head, in which case just go ahead and print the head. And OCaml has support for printf, just like C. So it can take format specifiers that you're used to. So %d is just the format specifier for integers. And this thing is just a helpful format specifier that flushes the standard out. So, and if you run this, we will get a function. And if you run it on an empty list, we get list is empty. If you run it on a non-empty list 1, 2, 3, we get head is 1. If you run it on a list with, again, this is just a list with 2, 3, 4, right? I've just written it in a mixing up syntax where here is a list with 3, 4, and I'm appending the element 2 to the front of the list. So I get a list with 2, 3, 4. So the head will be 2. Okay, so that's that. So pattern matching is sort of one of the most powerful features in functional programming, in particular OCaml and languages like Haskell, StarML, and so on. And the reason is that there is something that is very powerful when you use pattern matching, which is the compiler can check for exhaustivity. What do we mean by that? Patterns arise from the declaration of types, right? When the reason why we have the two patterns here is there is a list type which has a nil constructor and a cons constructor, and hence whenever you write a function such as this one, right, which matches on the patterns, the compiler can statically check whether you've handled all of the cases, right? This comes in very handy when you're building software, right? For example, here is the same function, but what I've done is instead of matching on just a head and a tail, I'm matching two heads and a tail. You can sort of see, yeah, so what I'm doing here, the list is non-empty and the second element is H2, right? So this is the head, this is the second element and the tail. So the thing that it does not match is a list with just a single element, right? It doesn't match a singleton list. This matches an empty list, right? This pattern matches the list with at least two elements, right? The tail could be anything, including an empty list. But what it doesn't match is a singleton list. And if I run this program, I immediately get a warning, right? This is not an error, this is just a warning. But the warning is very illustrative, right? So it says this pattern matching is non-exhaustive. This is compiler statically finding things out, right? We are not running it. This is statically the compiler says, here is a pattern that is not matched. In particular, it says that the pattern, which is any element const to empty list, is not matched. It is actually giving you a pattern. It's not telling you in English, but what it's saying is you are not matching singleton lists in this particular function, right? So that's a warning that you actually get for free from the compiler, right? And so that is exhaustivity. So it is checking for whether you've matched all of the cases, but you can also match too much, right? So in particular, if you have two cases that overlap in such a way that one of the cases is not used at all. Then you get an unused case warning. So here is an example. So I've added this match for a single head and arbitrary tail, right? The point here is this pattern subsumes this pattern, right? If you take a list with at least 2 elements, you can always split it into a list with one head and arbitrary tail, right? So any list will either be an empty list or a list with one head and an arbitrary tail. So when you call this function, it is one of these two patterns that are matched. You will never hit this pattern, right? So if you run this function, what you get is the compiler says that this match case is unused, because the compiler can statically find out that these are the two cases that will subsume all of the possible list values, right? And this particular case will never be taken. So you get an unused case warning, you know that this case will never be taken. So this is also useful. And I mean, we are sort of looking at it in the small, right? What does it mean for large software development? Imagine you have some program, right, that is like thousands of lines long, and then you have this data type which has like 7 cases, right? Some complicated data type, and you want to say change the data type such that it either has an additional branch or a fewer branch or something, right? When you change the data type and when you compile the program now, you will automatically get warnings and errors, right? The compiler goes all the way through, checks all of the functions for exhaustivity and unused cases, and you will get a very nice way of refactoring large pieces of code. Okay, um, so it's hard to see that this can happen just by looking at this example. But if you sort of build real software, I mean, we will sort of build larger examples where you will sort of encounter this particular case. Okay, so there is a question. The question is, OCaml uses %d in the print statement to infer the type, right? But what if we don't have the print statement? How will it understand the pattern? Okay, so the question is about this one. How will it understand this pattern? So if you don't have this, actually, if you don't have %d, right, and I have, say, h2 here, actually, OCaml is going to throw an error. The error is not easily debuggable because OCaml is sort of using some complicated mechanics to actually take a string and find out what is the pattern that is needed here. Essentially, what OCaml is sort of saying, to sort of throw away all of this, is it's saying, I don't have a format specifier which expects a single element here, but you are passing an additional parameter. Right, so that's really what it's saying. It is very rare that you will have to encounter this error, but if you encounter some error that says that you have some error in camel internal format basics, then the pattern is wrong. If you remove h2, then it's fine, right? If you remove h2, then it's fine, because so it's like printf some string, right? This is what C gives you, right? You can just printf arbitrary string, and that's similar to that. The reason why this works is a little bit complicated. We will sort of come to some of the pieces for making this work. But sir, how does it know if it is a list or an int? We are not printing anything, right? We don't have any format specifiers here. So print end line, I don't understand the question, right? So we are not using h1, h2, and t here. So this printf is like printf hello world. So OCaml knows that this is a this is just a
Sir?
yeah.
Sir, am I audible?
Yeah.
Yeah, sir, my doubt is like if we have H1, H2 and T, and if
Okay.
we have not specified anything
Ah.
about H2 and T, then
Yeah.
how?
Okay. Yeah, this one. And then remove this one as well. So what happens is it is left polymorphic. So does that, we are not specifying anything here, right? We are not specifying anything what H1 and H2 are. And what happens is OCaml infers the most general type for this. This function can be applied on any list, right? It doesn't have to be an integer list, floating point list. So what happens here is it is left as quote, this alpha type, which is polymorphic. Does that answer your question, Venkat? Okay. So the point is OCaml is going to infer the most general type, and then based on your use, it is going to specialize, right? So for example, I can't do, just to give you an idea, let's say I have H here and I have percentage F, H1 here, right? This won't work because this list is inferred to be a list of integers because of this use of percentage D. And percentage F is a floating point, right? So OCaml sort of says, okay, this is not sensible anymore. Good question. So I think, yeah, OCaml tries to infer the most general type possible all the time. And yeah. Okay, so moving on. Let's write some functions with pattern matching. So the basic way we write any sort of useful things in OCaml is we have some type definition. We write functions that work over the type definition using a recursive function, and that gives us all sort of useful things to do. Here is an implementation of length of a list. When you think of a list, the list is very similar to linked lists in C, right? This is what you would do in, if I were to ask you to write a linked list implementation in C, and then find the length of the linked list. So I'm asking for the length of the list. If the list is empty, then the length is 0. If the list is non-empty, right, H and T, get the length of the tail, and the length of the list is 1 plus that length. Okay, so this works. So this sort of, again, you can see that this length implementation works on any type of list, right? It doesn't matter what the content is because I'm not actually using the content in any interesting way. So I'm sort of ignoring H here. So that is why this function is generic, right? It is parametric over the actual type of element in the list. This is parametric polymorphism in practice, right? There is no STL like C++ templates or something. This is like baked into the language. You don't have to do extra work to get these sort of parametric polymorphism. It is just built in, and that makes it very easy to write programs. Okay. So yeah, but there is a problem with this implementation, right? In terms of efficiency. Yeah, it's not tail recursive, right? So I think Prajwal Prakash has an answer. Yeah, bunch of answers. Good observation. So what the problem is that, of course, I can have lists of length 1 billion, and I should be able to find the list of length 1 billion, right? If my memory heap has so much space, I should be able to find the length. But this particular function will stack overflow because you keep building the stack, and it will stack overflow because we are left with this +1 later. So we can turn this into a tail recursive one. So here is the implementation. Again, the same recipe we'll keep using, right? Whatever work we are left to do, we will always keep doing that in the accumulator and passing it, right? This is like a common recipe that will work for all of the, almost all of the programs. There are some programs which cannot be written in a tail recursive fashion, but here is one. So I define a length prime function that takes a list and an accumulator. If the list is empty, then I just return the accumulator. If the list is non-empty, then I recursively call length prime, the same function, with the tail, and then I do 1 plus the accumulator, right? So I sort of keep the pass around the count as an extra argument to this function, and when you reach the tail, you just return that accumulator, and the initial value of the accumulator is 0, right? So we define a So the reason for defining length prime is that I want to use length as a function name. So length L takes a single argument and then calls length prime with L and initial accumulator value 0. And this works. The previous one also works on this small list, but you'll stack overflow on a very large list. So here is the length of the list. So the other thing that is important is the patterns in OCaml are matched in the order in which they are written down. Okay, so here is an example. I am checking for whether a list is empty or not. Okay, so the implementation says, okay, if the list is anything, then it is non-empty. If the list is empty, then isEmpty is going to return true. Right. So the problem here is OCaml sort of reads the patterns from top to bottom. So this underscore pattern is the catch-all pattern, right? Yeah. So this will always return false because it is going to match with all the lists. The order has to be changed. So, but you get a helpful warning, right? In this case, it is useful because this matches all of the cases, this case will never be taken. So if you get a warning that the match case is unused, then it is very likely that your code has some issue, right? It is sort of hinting towards some logic issue. Again, this is sort of a meta thing that I'm saying. If you have a program where you get warning 11, the match case is unused, go and verify that your logic is correct, right? So here the logic is wrong, right? It has to be, as some of you have mentioned, it has to be like this, and this will work. And the warning has gone, right? Because naturally, both of the cases are used. Okay. And okay, so here is an implementation for list.nth. So the specification is nth takes a list and a index and returns some element if the index is less than the length of the list. If the index is greater than the length of the list, then we just return none, because if the list only has 2 elements and I ask for the element at position 10, I'm going to return none. And the way I'm going to do it is this, right? So I'm going to pattern match on the pair, right? Here is a use for the tuple. Okay, so there's a question. I'll just pause. Sir, then in the previous example, using float and int, it was showing that expected float, while float was defined afterwards. Yeah, type checking works differently, right? So good question. So you are asking, in this case, %d is used first and %f is used afterwards. But OCaml is saying no, sorry. So the way to read this is this, right? It's sort of looking at the cases from top to bottom, and it inferred that the type of h is integer, right? And so h1 also has to be an integer, right? But the pattern here is %f. So the thing that to go here should be a floating point number. So that is why it's saying this expression has type integer, right? h1 has type integer because the type was inferred from here, but the pattern was expected of float because this pattern %f expects a float. So yeah, so the type checking is going from top to bottom. Okay. So moving forward, where were we? This one. So here is a nice way of using tuples, right? So we are actually creating a tuple here, right? A pair, and then we are pattern matching on the pair directly. So what we are saying is pattern match at the same time on the list and this integer n, right? If n is 0 and the list is non-empty, it has a head, then the result should be some head, right? So if the basic case is I ask for the element at index 0 and the list is a singleton list, then you're going to just return the head, right? And if the list is, if n is anything other than 0, right? So take the head and the tail, and then recursively call nth on the tail and subtract -1 from n. So you keep remove one layer, right? You remove one layer of the list, which is throw away the head, remove one layer of the number, which is subtracted by -1, and keep calling the same function until you reach 0. I'm sort of assuming that the numbers are positive, right? Non-negative, but you can also handle that easily. But that's not the point here. And then finally, what you want is if you keep trying it apart, and say my list is 2 elements long, and then I have an input of index 10, right? What will happen is you will first throw away one element, number goes to 1. You'll throw away the second element, the number goes to 0, right? But that particular pattern cannot match these two cases, right? This will match a non-empty list. If in order to match this, then the number has to be 0, which it is not. So you'll take the third pattern where the list has 8 more elements still, and the number is 0, right? So in which case you return none. So we saw sum and none in the last class, right? So we said sum and none are this optional type. Just to remind you, so okay, I'll just finish this. So you get a function which is takes a list, takes an integer, and then returns a quote option, right? And it's a quote list, right? So it works on any valued list. And if I ask this, I'll return none because the index goes from 0, 1, 2, right? And stops at 2. This is 4. But if you ask for something sensible, I think I can ask for something sensible, which is 0. It gets 1. So this works. So Naman, I don't know whether you were in the last class. So none and sum are just this type, right? So none is an option type, and sum 5 is also a value of type option. The type definition itself is quote option. Sum is a constructor. Sum is a capital thing, right? So it's a constructor. So I mean, here's the type definition, just to remind you, right? So it's okay to ask these questions. So this is the definition of the type. So none is a constructor and sum is a constructor. We just use sum and none. So if you see capital letters here, then it's a constructor, right? So that's an easy way to identify whether something is a constructor in OCaml. And similarly, none is a constructor. Okay. So this is fine. So here is reversing a list. Okay. So again, we are going to directly write the tail recursive version. And we just write head. Head where? Venkat? Instead of some head. If you write head, what will happen? Right? So in the case when the index is going out of bounds, we want to return none, right? So all of these branches should return the same type of value. So this is returning alpha option, right? And this is returning alpha. And because this is a recursive call, it will return whatever the function return type is. These two types are not compatible, right? When I just return head, it is alpha. This is an alpha option. So if I run this thing, yeah, so okay. So so the issue is that, okay, so I'll tell you what happens here, right? This is the expected type. So I take some alpha list. I have to return alpha option because In the case when I find an element, then I return some element, otherwise I return none. But when I change this to head, OCaml tries to infer some type, right? The thing that has happened is it sort of infers the type. This is an incorrect function, but it infers the type where each of the elements in this list is an option alpha. So I will let you sort of figure it out yourself, right? So this is not the function that you want. So this function can be applied. So okay, so just to complete, right? This function can be applied on 1, 2, 3, and 4. If I change this function to head, then the expectation is that the input list is a list of option types. I cannot apply this function on this anymore, right? This will error out. So yeah, so in this case, even though OCaml is sort of inferring a type for this function, this is not the function that we want, right? I want a function that takes an alpha list. This is a function that takes an option alpha list. The problem here is that because this is a none, it's a option type, and it assumes that the head must also be an option type, and that is why it infers the type alpha option here. But this is not what we want, right? We actually want this one, which gives us the correct type. Good question. I want you to sort of work through it, right? So this is not the function that we want. Okay, just moving on. So we are going to write reverse of a list, and we are going to directly write it in tail recursive way. You can also write it in non-tail recursive way, but this is we will usually not write non-tail recursive one if there is a tail recursive one, right? So the way you have to always think about this is the way you think about induction, right? The induction that you've studied in your discrete math or logic courses. You always think about the base case and the inductive case, right? What is the reverse of an empty list? The empty list reverse is an empty list, right? So if the list is empty, then you just return the accumulator with the idea that the initial accumulator will be empty, right? And if the list is non-empty, has a head and a tail, then reverse the tail of the list, right? And the accumulator, you push the head to the front of the accumulator. So what will happen is that because the initial accumulator is empty, you will first push 1, right? If the input list is 1, 2, 3, in the first call, this will be a singleton list with 1. And the second recursive call, it will be 2, 1. And in the third recursive call, it will be 3, 2, 1 because you're pushing always the head to the front, right? And finally, when the L becomes empty, you return 3, 2, 1 to be the result. So yeah, this is perhaps the first non-trivial tail recursive function that you've seen. And as we do, we set accumulator to be empty here, right? And reverse of a list takes any list and then returns some list. And we can ask what is the reverse of 1, 2, 3? It returns 3, 2, 1. So the important bit is here, right? Just to go through here, the first time it matches 1 here, right? It will be 1. Sorry, this will be 1, and this will be 2, 3, right? And here the tail will be 2, 3, and the head will be 1, right? In the second recursive call, this will be 2, 3, right? So it will be 2 colon 3, right? This will be 1. So the tail will be 3, and you will push 2, 1 here. And third call, this will be just 3, and the tail will be an empty list. Tail will be an empty list, and you will have 3, 2, 1 here. And this call will match this pattern, right? L is this tail becomes this L here in the recursive call. So you will match with the empty pattern. You return the accumulator, which is 3, 2, 1. Okay, so That is why this algorithm works. Any questions on this? Just write it down. I think that's sorry. That's the way. Work through. If you're unclear, just work it through an example, just like I did, right? So, and I think you will get it. If you don't, so one thing I would recommend is if you have any questions on these materials, you can also ask in the Slack channel, right? So either I or your friends will answer, and feel free to ask questions, right? I think um, yeah, I mean, this is like a standard thing that people say. There are no stupid questions, so always ask questions, um, and uh, and either there are a bunch of people who can help. Either I can help, or the TAs will sort of answer your questions, or your friends will answer the questions. So yeah, so always ask questions. So if you have any questions, please do ask. Don't hesitate to ask questions, right? Only by asking questions can we actually learn and improve. Um, yeah, this particular mode of teaching is not conducive to asking questions, although some of you are asking questions nicely. But if you have questions that you don't want to ask publicly, just send me a direct message as well, right? I will respond to the direct message as well. Okay, so moving on. So here is an implementation of append. So OCaml has a built-in operator for append, right? So this at operator is append, and you take two lists and it sort of concatenates both of the lists. So the result you have is 1, 2, 3, 4. This is not magic, right? So you can implement this function in 2 lines, actually 1, 2, 3, 4 lines. And the way you do it is you have L1 and L2. Append takes two lists, right? It takes the list L1 and the list L2. Again, you apply the principles of induction, right? If L1 is empty, then append of an empty list to L2 is just L2. So you return L2. If L1 is non-empty, then there is a head and a tail, right? So you append the tail of the list to L2. So it is going to return some appended list, and the head goes to the front of that, right? So, and this is append essentially. This is not tail recursive. You can write a tail recursive version. It's it takes try to write a tail recursive version of append. Um, yeah, it requires a little bit of thinking, but it's sort of fun. You might want to use reverse if you want to use tail recursive append. So okay, so we've defined append, and we have two input lists, right? Two are alpha lists, and it returns an alpha list. And if you pass 1, 2, 3, 4, 5, 6, the result will be 1, 2, 3, 4, 5, 6. I'm just writing it this way, but you can also just do. Okay. Okay, so those are some examples of pattern matching applied to lists. And my intention of teaching that was twofold, right? First one is how to work with pattern matching, and the second one is how to write simple functions over lists, right? So you can imagine building a whole list library. In fact, OCaml has a list library. The compiler itself gives you a list library. All of the functions are written this way, right? So it so happens that when you write OCaml programs, there is only a few ways in which you can write the correct programs, right? So if you start writing your append function from scratch, it will most probably look exactly the same letter to letter to what we have in the standard library. And this is one of the good properties of OCaml, right? So because the programs are so succinct, you just get the ideas across. A lot of the boilerplate is just gone. There is very little boilerplate, in fact. So okay, so that's simple pattern matching. You can also pattern match on complex patterns. In particular, you can pattern match on nested patterns. So we go back to our original definition that we had seen in the last class, right? So we have colors red, green, and blue. We have points which are 2D points which use a record, and the labels are x and y, and both of them are integers. And we have three kinds of shapes. We have a circle which has a center and a radius. We have a rectangle which is defined by lower left and upper right points, and we have a color point which is a point and a color. Okay, so we define the type, and so we are going to do nested pattern matching. In particular, we are going to write a function which is going to return true if the first shape in a list of shapes is a red point. Okay, so the input is a list of shapes, and if the first shape is a red point, then we return true, otherwise we return false. Okay, so we pattern match on L, and then we are pattern matching here on multiple things, right? So firstly, we are pattern matching on a list. We are pattern matching on a non-empty list because I'm using cons here. There has to be a head and a tail. I don't care about the tail, that is why I'm using underscore here. In the previous examples, we just used HD head, right? But you can also make it more complicated. This can also be another pattern. So the pattern that I'm using here is color point, right? Just to recall, color point is defined here, right? And color point internally has two arguments, right? It takes a point and a color. I don't care about the point. Actually, the specification is check whether the point is red. Actually, red circle, red point. Okay. And I want to check whether the color is red. So I actually use the definition of red from here, right? And if this pattern matches precisely, then I return true. Otherwise, I return false. So the point note here is there are two levels of nesting, right? Actually, depends on how you define nesting depth, but there is one here for the list pattern matching, right? I match on cons. The second one is I pattern match on shape. I'm matching here whether the shape is a color point. You can sort of read it as having a bracket here if it makes it easier to read. I'm checking whether the first element is a color point, and then internally I'm matching whether the color is red. So you can happily do deep patterns, and OCaml will check exhaustivity check for these deep patterns as well. And this check is exhaustive because the second option is matching on all of the points, right? So this particular function, this pattern match is exhaustive. And the type that you get is again inferred, right? Just by writing this particular pattern, I am telling the compiler that this is a list of shapes, and it's going to return a bool because I'm returning true and false here. Okay, so that's the example of nested pattern matching. And yeah, here is one more example. So I'm going to, so it takes a list of points, and I'm going to print the coordinates if the point is green. Okay, so it's going to take a list, right? Print green point is a function, recursive function, because we are going to iterate over all of the list. If the list is empty, then there is nothing to do. I just return unit. Think of unit as the void value, right? So if there is nothing to return, you just return unit. If the pattern is a color point, right, and the color is green, then I get XY, right? I can pattern match records by using the variable names XY, label names XY, right? And of course, this is a list. I'm pattern matching on a list, so there'll be a tail as well. Why not a list of color points? Let me finish this and come to that question, right? And in that case, I'm printing just the X and Y, and I'm recursing on the tail, right? So this is a case where this is a list of color points, and I'm recursing on the tail. If the pattern does not match, then I still recurse on the tail because it could be a circle or a rectangle or a color point whose color is not green. So it could be a point with red or blue. In all of those cases, we simply recurse on the tail of the list. Right? We keep iterating or recursing over the tail until we reach the end of the list. So if you have a rectangle, a color point, a circle, there are two color points which are green, right? There is a rectangle and a circle. And the expectation is that this will print the coordinates 0, 0 and 4, 6. So, yeah, okay. So, yeah, it prints 0, 0 and 4, 6. So, Naman asks a question, why not a list of color point, right? But color point is not a type. The type is a shape, right? And color point is one of the shapes. So we cannot, so we can only describe a list of values of a particular type, right? And we don't have any means of just saying color type, color point is a shape. The way, if you wanted to just have a list of color points, you want to define color point as a type, right? And then you can say list of color points. But that's not what I'm asking here, right? I'm sort of using the shapes as a list. Does that sort of answer your question, Naman? Okay. Okay. So, so the thing that I'm using here is semicolon, right? I'm sort of using semicolon here. The question is, when can you use a semicolon? So this semicolon is semicolon for the list, right? So we won't care about this. This is like just using comma in a list in Python, but we just happen to use semicolon in OCaml. I'm talking about this particular semicolon, right? This is an expression, semicolon, this is an expression. This is a sequencing semicolon. So do this and that. But we sort of I was trying to tell you all about everything is an expression, right? And we don't have commands and so on. But when you use semicolon, you're sort of saying do this command first, and yeah, Saptak has the right idea, right? So do this command first and do that command next. So when can you use a semicolon? We can use a semicolon um, when the expression itself returns a unit value. So the OCaml is a language which has side effects, right? So again, I'm using the term side effect, but you can sort of see, you can sort of take that term as it can do other things than just running expressions for a value. It can print to a screen, send messages, and so on. So typically, when an expression returns a unit value, you are running it for some effect, right? And the effect that I have here is printing to the screen. So I can write print end line hello world. So even though it returns a unit value, it is doing some effect which is writing to a screen, and hence I can use semicolon here, right? I can write semicolon this expression. So this whole thing, in fact, happens to be an expression, and the value of this expression is the value of the last expression here. So the equivalent way of writing this would be just saying something like this: let unit equals print end line hello world in E, right? I'm using unit here because I know that the whole thing here will also return a unit. But the latter is considered the better style. So we tend to use semicolons here. So just to show you what will happen if you, I'll go here. So I said, as Satak also mentioned, um, you can use semicolon when the value, when this expression is evaluates to a unit type. But what happens if I don't have it as a unit type? So let me just do this, right? 5 is not a unit type, it's an integer type. So OCaml does not throw an error, but it does throw a warning. It sort of says what I just mentioned. So this expression should have unit, right? It's not a unit value, it's an integer value, but you can still run this program. It's not considered good practice to do this. Sometimes, invariably, your expression, you might call a function, right, for some effect which prints to a screen or something, and then returns the number of characters printed. If you don't want the number of characters to be throwing this warning, if I just call that function which prints to the screen, but also returns an integer, you'll get a warning like this. You can use this function called ignore. You can ignore the result of that function. So ignore sort of eats whatever type there is and then returns a unit. And you can imagine how ignore will be returned, right? So again, this is not magic. Ignore is just this function which takes arbitrary values, ignores it, and then returns a unit value. So that is precisely the type of ignore. Ignore happens to be a built-in thing, but if you look at the definition of ignore in the standard library, it will be exactly this particular sequence of lines. So ignore is a function that takes arbitrary values, right? It's an alpha value, so it can be applied to anything, and it returns a unit value, and that satisfies the type that we expect for semicolon. So so in OCaml, you will find a lot of these idioms, right? Ignore is an idiom. Ignore is not a primitive. And all of these idioms, you can sort of break it down and define it yourself. So nothing is magic. So in languages like Java and C++, there is a lot of magic going on. I'm not saying there isn't magics here. Yeah, you can, if expression is return unit, we can do so. Sorry, so I was reading an old comment. So there's a lot of magic in OCaml also, but not as much magic as C++ and Java. And hopefully you can sort of see, building from first principles, right, what an ignore function should be. A question I might ask is, I could have asked you, write down a function ignore, right? And you should be able to sort of work from first principles. So ignore is a type, ignore is a function that is applied to arbitrary values, and it has to return a unit value. So here is the function definition. So try to sort of go to the depth of what these expressions mean, right? And most of these are not magic. These are just like syntactic. These are just helper functions defined over the primitive features of the language. Okay, so let me erase this. The next thing we will see is exceptions. I'll just give you I have 2 minutes, but I'll just sort of introduce it. We can come back to it again tomorrow. So far we've seen pattern matching, right? And I don't know whether you've studied exceptions in C++. Did you study exceptions in C++ in your previous courses? Yes, no? Can somebody type an S or no? Yes, okay. Okay, good. So we have exceptions in OCaml as well. They're very similar, right? The runtime semantics is very, very similar. So you throw an exception, it will be caught by some handler, and then you can handle these exceptional cases. But in OCaml and in other functional languages as well, exceptions are mostly just variants. And their runtime semantics is the same as C++, but the static semantics is quite the same as what we've just seen with data types and pattern matching. So here is a declaration of an exception. So I'm defining my own exception. Okay, so I'm defining my exception of string. The way to read this is the constructor for the exception is my exception, right? And it is parameterized by a string. Okay, and OCaml top level says exception my exception of string. It just says you declare an exception my exception. And in fact, when you construct an exception, it's just a value, just like other values 5 and 3 and other things that we've seen, color points and so on. Exceptions are just values. And the thing to ask next is, oh, if it is a value, what is its type, right? Here, what I'm doing is I'm actually creating an exception instance, right? This is an actual use of the my exception constructor in order to construct exceptional value, and I'm just storing it in V just to show you the type. And the type happens to be EXN type, right? And this is primitive in OCaml. EXN is this primitive type in OCaml that encompasses all the exceptions. You can keep defining new exceptions, and all of these exception values all have the same type EXN, right? And we've seen algebraic data types, right, where we defined these shapes, circles and rectangles and a color point. So there, when we define the type, we have three variants, and those are the three variants that we can have in the program, right? If you wanted to add a variant, you have to go to the original definition and then add a new variant. Maybe I want, say, a square. I can add a new variant there. Maybe I want a pentagon. I have to go there and add it. But exceptions are what are known as extensible variants in OCaml. We won't look too deeply into this. Again, I'm not going to say much about this, but it's just a way of saying you can keep adding more and more variants for this, more and more constructors after the fact that you define the first one. So there is a built-in one, and then if you keep adding your own exception types, they just keep adding to the same type. So the type of exception is being extended with more and more constructors, right? New constructors of this type can be added after the original declaration. So that is what has happened here. There are a few built-in exceptions, and we've just defined our own exception here, which we've added. Okay, so I'll stop here. We'll sort of see more exceptions in the next class. Any questions on this? If you have any questions, I will also answer questions on Slack. So we'll continue with exceptions tomorrow. Thank you very much.